So today we are going to do section 3.5. First, let's look at the book. Okay, that's the page that I already scanned earlier, but I suppose let's look at the new part a little closer. All right. Next, page 106 and 107. Let's see, let me line this thing up. Okay, that should be close enough. Let's see, why is this thing not parallel? All right, and then a little bit closer on top. Okay, and a little bit closer on the bottom. All right. And finally, page 108 and 109. Let's see. This side seems to be fuzzier. Maybe I move over a little bit. It seems wobbly. Let's see. Okay, and then zoom in on the top a little bit. Why is that side seems foggier somehow? Yeah, not sure. Anyway. Maybe I'm tilting it wrong. Okay, that should be good enough. Now, so let's start section 5. We're talking about surface theory. Now, this section, we mostly round up everything we've learned about surfaces up to this point, but we are going to summarize it in an organized manner so that we know what we're talking about. Okay, so a surface, as we can remember, is so far we have learned how to describe it in these three main ways. There's actually even more way than that maybe, but anyway, the three main ways is the way number one, where you can use one variable, usually the third one, as a function of the other two, right? And then the second function, we just round up all three variables equal to 0, and doesn't matter who's the independent, who's dependent. And then the third one is a parametric form where we have the u and the v, and then those two things move around to describe our surface. And as an example, of course, the most famous example would be the sphere. Okay, a sphere with the radius rho we can describe it as the third coordinate being the square root of something, or just have them all squared equal to rho, or has the parametric form where we have rho cosine, cosines, and cosine sine, and so on. So all these three are familiar. Of course, the first one, the one with square root sine, the book didn't mention the negative part, but for the bottom of the sphere, you're going to need the negative part, right? Because being that you use the square root, you only represented half of the sphere. And the parametric form, it just happens that the u and v happens to be the latitude and the longitude. Well, anyway, that's a small piece of side information. Please think about that until you realize what that means. And so please read that yourself, okay? That is just a rehash of the past. And then let's look at the next page. Page 106. Now, page 106, we have a graph. Again, it's familiar from previous sections. We have a surface here, and what we're interested in is the tangent vector and the unit vector, and also the curves along well, this is talking about the parametric form. So the curves on the graph, as we hold one of the variables u or v constant, then we have two curves, right? If one of them is held constant, and then from there we get the partial derivative, which happens to be the tangent line of that curve that we are holding constant. And then if we take the cross product of the two tangent lines, then we get the normal to the curve. And now, see, here's the normal. This letter is pronounced zeta. I guess. Anyway, so this is the tangent to these two, this is the normal up to the surface, which is the cross product of these two tangent lines. Okay, and then, well, under certain conditions, of course, such as they're not zero or something. And so, assuming something isn't zero, or the cross product isn't zero, then we can come up with a normal. Okay, this is the unit normal. In fact, it's called the normal vector, but it means the unit normal. And so if you take, and the details of this is mentioned on page 77, but let's just believe that we did it and not even worry about looking it up. To save time. So the zeta, which is the unit normal, can be calculated as a partial x partial u cross partial x partial v. And that would be, that's in the parametric form of the surface. That's how you would calculate the normal. All right, and so let's go on. And so please read over this yourself carefully to refresh your memory. None of this is new exactly, but we learned it in bits and pieces in the past. So the book is rounding everything out very nicely, so we have a concrete and complete idea of surfaces and their normals and the tangent plane and all that stuff. Okay, so let's continue to page 107 on top, where the surface is, so we have three equations for the same surface, right? Back on page 105 in the beginning of the section, here are three surfaces. So that's a surface that, I mean, not three surfaces, three representations of the same surface. So this is representation 1 and 2 and 3. So let's look at what happens with representation 1. Now, if the surface has equation 1, I'm at the top of page 107, then of course x3 is f of x1, x2, and we'll let x1 equal to itself and x2 equal to itself, such that to use the formula to the theorem 6 on the previous page, we'll let u equals to x1 and v equal to x2. And then we'll take the cross product and figure out what that zeta, the normal, is. So when you do that, you can stare at this thing and do it real quick in your head, being that x1 is just, u is x1, v is x2, so the derivative, you can come up with it very quickly, okay, which is 1, 0, f1, etc. And then when you take the cross product, it'll be something like this. That is zeta equals to minus f1, minus f2, and 1. If that looks familiar, that's because we did that before. But it doesn't hurt to do it again. So please do that cross product real quick, okay? And then we come up with this. And it's divided by some kind of a length to make zeta the unit vector. But in this chapter, we're not going to care how long zeta is, because we're mostly going to calculate the tangent plane, so that we only need zeta's direction, okay? And we don't care how long it is, so we'll just let it be as long or short as we want that is convenient for us. And yeah. Anyway, so that's for formula 1. That is equation 1 of the surface. If the surface is in that form, then the normal vector will be as given, f1 minus f2 and 1 divided by its length or something. And then, so next, what if the surface has equation 2, which is the big F of all three variables symmetrically equal to 0. We don't care who's independent, who is dependent. Now, in that case, then we can do a similar calculation, which we have done in the past as well. So please do that, redo that yourself. Okay, I have it done here. That is, this is just what we've done, in fact, many times. Back in, when did this happen? I have written down here, page 24. That's a long time ago, right? And this is from Theorem 7, page 24, where you calculate u equals to, right, well, whatever. U is x1 and v is x2 again. So then with that, you do partial u, partial f, partial u, and then partial f, partial v, and figure out what f1 and f2 is in terms of big F, and then plug it in the same way. So then by the time you take the cross product, you end up with this thing right here, this thing where zeta equals to the f1, f2, f3 vector divided by some proper normal, some proper magnitudes to make it a unit vector. But that is basically how we did this. We did this many times, but please do it again, okay, to refresh your memory. So that's but in any case, that's how we came out with this stuff. And which is, yeah, we did that. Wow, that was such a long time ago, doesn't it? Anyway, so that is the equation 2, and the normal formula for equation 2. And of course, the normal formula equation 3 is just given in theorem 6 of the previous page, where the theta is xu cross xv. Okay, so then next let's look at section 5.2. We're still on page 107, where we can write down the equation of the tangent plane, okay? Because is now the tangent plane is just standard, so we might as well write it down. And so the equation of tangent plane to surface 1 is following the formula for any plane, tangent or not, okay, which is on page 67, equation J. Yeah. So anyway, the equation, I think I'll show it to you right now. Okay, I found it. This is on page 67 of the book. Look at statement J, okay? The plane through some point R with direction A for the normal has equation x minus r dot A equal to 0. All right, that translates into exactly into this equation if you think about it for a few seconds, okay? So remember x minus r is this point right here, okay? X minus r equals dot A is that normal. Where's the normal? Right here, okay? And once you do that dot product, and then E equal to 0, which just means that we moved some of this stuff around because these things are negative. So you put the negative stuff to the other side of the equation, and that is the dot product for the plane equation. So please think about that a little bit until that makes sense to you, okay? But I will now move on. And then that's for equation 1, to find the tangent plane if your plane is presented as equation 1, where you have an independent variable as x3. Now, if your plane is as equation 2, where you have a big F of all 3 variables in equal standing, then the tangent plane is with a similar equation, where now our normal is defined here, right? And remember, we don't care what the magnitude is, because we only care about the direction in the dot product, being that it equals to 0, right? So the magnitude means nothing. And so we take the dot product then of the normal as the equation that I just showed you. See, you subtract by the point, and then dot the gradient, which is that, okay, because that's the normal, and that equals to 0, and that will give you the tangent plane. And yeah, and we've done this before, so please go over that yourself and look at page 67, statement J, to refresh your memory if you have forgotten about this, or if it feels a bit fussy. Okay, just stare at it long enough and you'll get it. And then and finally, the gradient. What if we had the parametric representation where x is represented as u and v? In that case, let me see. That is the third representation, x equal to x of u and v. In that case, the tangent plane will be this thing right here, where this is the determinant, okay? If you write down the determinant of this thing, that will work out. Now, let me see if I wrote something. So I wrote down a quick some notes on that. Okay, there are some notes from what I just mentioned. But anyway, so to figure this out, what happens is we go by the definition, which is a plane is defined as x minus a, x minus some point a, or vector a, dot the normal of the plane equals to 0, and that's the definition. But the normal theta is equal to xu cross xv, right? So in other words, we have x minus a dot xu cross xv equal to 0. That is another way of saying the determinant is equal to 0, because that was given when you have r dot s cross t. That is the same as RST determinant written. So that's what we mean by here, and that's how we got that. So next, let's look at section 5.3, the normal line. The normal line is, of course, the line that follows the normal vector going through wherever point that we want to calculate the normal of, okay, at some given point. For equation 1, that is the one where x3 is a function of the other two, then we have following, we already know what the normal vector is. So by the formula of a normal, of a line, which is given on page, okay, maybe I should show you the formula first. Okay, this is statement M on page 67, where we talk about the line, right? The line with direction A is x minus r, where r is some point, equals to TA. Now there is another form, it's called x minus r cross A equal to 0. But I don't find that to be very exciting. Like, why would you want to do the cross product? And so then the normal line, then following the dot equation with t in it, then it translates into what you see here, where x1 equals to whatever. Okay, and that's because the normal, as we calculated for the normal, following the normal vector, is already psi is given here, right? We don't have to pay attention to the d because we're done something. Well, anyway, yeah, we only care about which way it's going. So that's why, so the d is ignored, and we end up with these three formulas. So, and let's see, I think I also wrote this down to make sense, but I don't think I wrote anything different from what the book already said. You just, so psi is equal to that, which eventually means if you follow the formula for the line, then you get the same thing the book has. All right, so that's for equation 1. Now, if your surface is in the form of equation 2, then the normal, then you can use that cross product representation. Okay, here's on the same page. Remember, there is a cross x minus r cross A equal to 0, so you plug that in, where A in this case is the normal to the well, aren't we talking about a line here? Well, whatever. Okay, that's the cross product representation, but I don't find it to be very exciting at all. I mean, then you got three equations for a line, really, and so let's not bother with that if we can help it. So then I think this one, the one I wrote after that, x minus r equals t zeta, seems much better. Okay, then you can, because with the parameter t, then you can type that thing into a graphics calculator if you need to. So that is that. But the cross product does exist, I guess. Yes. Anyway. Now remember that the reason it works well is because when the cross product of two vectors are 0, that means they're parallel, which means the line is going in the same direction as, does it mean they're parallel? No. Right, they're parallel, right? So that's why, so the cross product equal to 0 is a thing, but I don't see how that can possibly be interesting. Well, but we'll keep it in case it is. Okay, so that's so the last one option is option 3, where x is the parametric surface with parameters u and v, and in which case we do a similar thing. Yeah, I didn't write that down, but anyway, so then the normal to the surface, we're still talking about the normal here, would be following the equation, the same equation. Then we have and then psi in this case, of course, is the xu cross xv, right? See the very top of the page of my notes here. Then you plug in the same, well, x minus r equal to t times psi. Which, so you write that in, and that's what this says, okay? This is, so then x equal to the original point plus t times the psi, okay? Ignoring the magnitude, because we don't care about it, because we only care about the direction. Okay, now let's look at the next page, page 108, where we consider some example. Now, this is, again, a familiar example in Calculus 3 or something, that you at one point calculated some circular cone intersecting with some sphere, okay? Yeah, if you remember what that looks like. something like this. Okay, you have a sphere, right? And then your cone, which is centered, and the intersect and stuff like that. If that were to happen, then the intersection just happens, and no matter, as long as they're both centered, as in the vertex is at the origin, then the cone, regardless how wide it is going to intersect at an orthogonal. The intersection will be orthogonal or perpendicular. And to prove that, then all right, to prove that, we need to calculate something. Where is it? All right, so to prove that, please do this yourself too. Okay, we have the sphere, and we're gonna prove. Basically, we're gonna find out the two normals at the intersection, and then prove that their dot product is 0. Therefore, they're perpendicular. So we calculate xu, xv, do the cross product, which equal to this, and that will be called theta. Okay, and then for the cone, we do the same thing. We calculate xu, xv, do the cross product. This is called theta bar. At least I think that's how it's pronounced, with a line on top. So that's the normal for the sphere and the normal for the cone. And then we figure out that the intersection is exactly when u equals to alpha in the equation of the sphere, I think. Yeah, or no, well, whatever. Okay, u is alpha in one equation and u equal to rho in the other equation. Anyway, so that would make it the intersection, because then the two formulas are exactly the same. Now, when that is true, if you take the dot product of side cross, side dot side bar, then you will come up with 0. That is, you would dot this thing with that thing. Okay, with this condition given in each situation. Anyway, there's a bunch of details. Please verify that yourself. It's something that we've done something like this before, okay? But it's good to do it again to I don't know, to do something, because the book did it, so therefore we're gonna do it. And so please do this yourself. I will show you again in case I didn't show it perfectly the last time. Yeah, that's good enough. And so with that, we have come to the end of this section. And so for homework, okay? Let me get the homework ready. So for homework, please do problems. Okay, I'm not done typing yet. Let me finish typing. Okay, for homework, please do on page 108, please do problems 1, 2, 3, 5, 7, 8, 9, 11, 12, 13. Yeah, that looks right. All right, and we are done. I want to talk about all of them. Okay, now that we're done with the homework, let's talk about problem 1, where we're supposed to find the tangent plane and the normal line at some point of some surface. Okay, so we do that. That's a generic problem with a slight difficulty in taking the partial derivative, because you have variables to power of variables. Okay, and to do that, you just have to remember this thing right here, which is not done very much, so it tends to be forgotten. But once you remember this formula of how to take derivative of something where x is on top, then you're okay. So and then yeah, so then you figure out what all these things are. And then, so which gives you grad f, okay, which is the normal, and then everything will, the tangent and the normal should come out very nicely. That's problem 1. Now problem 2 says when is the tangent plane parallel to something? In other words, when is the tangent plane of a certain value? Right, that is, the normal has a certain fixed value. So when is the tangent parallel? Okay, so then problem 2, then we have first, two planes are parallel if their normals point to the same direction, right? In other words, the unit normals are equal. So then we have, and anything that's parallel to the plane x1, x2 has to be it must have a normal of 0, 0, 1 or 0, 0, b, where b is a constant value. So then f, well, here's our ellipsoid, which I wrote it in the big F format, okay? And the normal being F1, F2, F3, I calculated it, and it becomes and it has to be equal to 0, 0, and a constant b, where b better not be 0. And so if that's the case, then we're going to calculate then we're going to solve for, we need to know what point it is that this happens, right? So we're going to apply Cramer's rule, where I calculated determinant over here with the determinant calculator, because I'm not about to actually do a determinant. And anyway, so the calculator gave me this number for the this particular determinant, okay? And applying Cramer's rule, then x1 then equal to, by the time you get through the calculations, which is minus b over 18. Okay, b is, well, whatever it is. B is flexible, I think. As long as not 0, is acceptable. And similarly, I calculated x2 and x3, which equal to something to do with b. Okay, x1 is that, x2 is the same, and then x3 equal to this thing. Right. And then what? So once I have that, I have I still need to calculate the 2 points, right? So the 2 points is where I have to plug it in. In other words, what are the values of b? The reason I have t here is because I decided to call b t. I thought maybe that would be better, but it didn't turn out to be, I don't think it turned out to be any better. Okay, it changed nothing. But in any case, my point is that, but we need to calculate what it is, okay? So we plugged it into the ellipsoid, right? And then solve for x. And so let me show you what I did. Here's what I did, okay? I plugged it, I used the online solving calculator, the algebra calculator, I think it is. And then I plugged in b equals to, b now it becomes x. So x over 18, b over 18, I plugged it on, and the third, and x1 is b over 18, x2 is, negative, x2 is negative b over 18, and x3 was 15 b over 54. Yeah, anyway, so once I plugged all that in, and then I clicked the solve this equation, and it showed me the x equal to 11 point something, but I ignored it. Okay, we'll just take x equal to 11 or minus 11. That's the other value, but we'll focus on one at a time. So then, so if x equal to 11, then the 2 points, but we need to take 11 divided by 18 and stuff, right, to calculate x1, x2, and x3. So the 2 points then becomes these two. What is that, minus? Is there a minus there? Yeah, I guess there's a minus there because of the negative. So then the 2 points are minus 0.6, minus 0.6, and positive 3, and then the negative version. Yeah, okay. Anyway, so because t or b has 2 values, so that's just to calculate the intersection point. Right, and then what were we doing again? I forgot what we were doing. Let me see. Problem 2. At what points are they parallel? Yeah. Okay. So we found the points. Okay, they're parallel because that's how we calculated the 2 points. Now and then I graph this thing. I think. Yeah, I would like you to graph it if possible. Okay, graph problem 2. The reason is because I think it looked nice. Here is, yeah, because we don't have the answer to problem 2, right? So the graph, as you can see, there's the line. Is that what? Anyway, this is the ellipsoid, right? This is the line, I guess. Right, and you can see that the line, the tangent plane on both dots, right, where the line crosses the ellipsoid, does look horizontal, right? It does look parallel to the xy plane or x1, x2 plane, which is comforting, being that we don't have the answer, and the answer we do have looks good. So that is always a pleasant thing. Right, so that's what I have here. I plotted the ellipsoid, the line, and the 2 dots, okay? And you can see the 2 bumps there on the line. Those are the intersections, so everything seems to check out, so which is nice. Okay, so that's all I want to show you about problem 2. Okay, problem 3, we need to figure out we have a curve and a surface. We need to figure out where they meet. So we do a bunch of algebra, okay, and come up with, I think, some points, I guess, where the curve where the curve meets the surface, and then we calculate the tangent of the curve. And what is that? That is the normal to the surface, okay? And then figure out that one of them, the tangent and the normal are perpendicular, because the tangent is this one at one of those values, t equals 0, I think, is 2, 0, 0, and the normal is 0, 0, 1, which means their dot product is 0, which means they're parallel, and therefore the angle between them is 0. And that is just a routine job, right? You follow the formulas. So I'll show it to you here. And so that's that. Next, let's look at problem 5. And problem 5 says the surface has 2 tangents, okay, at some point. And we need to find both tangents. Okay, so, but first we need to find the at 1, 0, 1. First, we need to find out what is the parametric representation. That is, when x1, x2, x3 equals to 1, 0, 1, what is u and v, right? And so let's do that. So we do some, detailed work. So once we calculate this situation where each one equal to 1, 0, 1, and from there we can calculate what is v and what is u and all that stuff. And so once we got that, then we can take the partial derivatives at those values and figure out what they are. I already took partial derivatives here. Then once we figure out what u and v are, then we can plug it in to figure out what the partial derivatives are, which I got it over here, 2 cases. And because the way sine and cosine, I end up with two possible values of sine v, which plug it in, give us two normals, okay? Because xu cross xv is the normal, so we end up with 2 distinct normals. And with the 2 distinct normals, if we plug it into the formula for calculating the equation of, what are we doing again? This is planes, right? 2 planes. The 2 planes, the formula is given as such in the previous page or something. And so this is plane 1 and plane 2. And then that gives us 2 equations of 2 planes. Now my answers here don't look exactly like the answer in the book, but they are the same plane if you, it's just you need to multiply something to adjust. And so that the coefficients are the same. So that is, that's how you do this. Okay, I'll show it to you again in case I was not clear. Yeah. And anyway, so that I thought that was quite interesting. That why does this thing have two tangents at the same point? So I plotted it out on the Desmos calculator, and that explains it. Okay. The reason, you see that blue dot there on the red surface, that is the point. The reason there are 2 tangents is because the surface crossed itself at that point and alongside. Okay, so then that's why we have 2 tangent planes on the surface with the same point. And the surface is parametric, and parametric surfaces you can do a lot, okay, including getting them to cross and wrinkled and whatever. And there's a lot of freedom to parametric surfaces. And so then that is, and then over here I plotted the 2 tangent planes. As you can see, Desmos did a pretty good job of plotting it. You notice that it really is a tangent plane. All right, so that's what it looks like. Okay, and that's all I have to say about that. So. Okay, next let's look at problem 7, where we have a cylinder with its axis along the x2, that is the y-axis, and then we need to figure out the equation of the tangent plane of the cylinder at some fixed point by representing the tangent plane in all 3 forms that we have gone over in this section. So let's do that. Now, the tangent plane in the first form would be z equals to something about x and y, which end up being just x3 equals to a squared minus x1 squared because, well, yeah, because it's a nice comfortable cylinder. So then where x2 is not in the equation, okay? We don't care what x2 is. x2 can be anything. And therefore, if we take the partial derivatives of f, according to the formula, then we have all that stuff where f2 specifically is 0. So then we can write down the tangent and plugging in the values for the f1 and f2, then and following the formula for the tangent plane, then we quickly arrive at some sort of answer right here. So that's surface type 1. Then next we represent the same surface with a big F, okay, with all three variables in equal position. Well, in that case, we calculate then the grad f, and then plug in the suitable values, plug in the tangent plane equation, which end up being the same thing, okay? It just looks just like that by the time we're done with it. And the third option is we have to represent that cylinder in the parametric form, which if you stare at it for a while, then you eventually realize that we should probably do a cosine v, a sine v, and then for the two coordinates, and then x2, being that we don't care what it is, so we'll call that u. Now with that, then we again calculate xu cross, calculate xu, then, well, figure out what u and v are, okay, for that particular point that we're talking about, what this u and v has to be. And once we got that, then we calculate xu, xv, and then apply the formula for the tangent plane, which is the determinant which is the determinant of these things. This formula is in the previous page, and then we just and then once we calculate the determinant, we notice that this is the exact same equation as this thing. All right, so therefore it gives the same equation, and that means we should be good. And that's problem 7. Next, problem 8 is, problem 8 is where we rotate some curve. Right, remember the good old days when we did the volume of revolution? Yeah, weren't that? And those comfortable days. And so we are going to do something similar here, okay? Except that what are we doing? We're calculating some tangent or normal or something. What is this? Problem 8? Yeah. So a curve is being rotated around the z-axis, the x3 axis. Then the normal line of the surface is going to cross the x3 axis. Okay, just the way it is. If you think about it, it makes sense. It either crosses the x3 axis, or if it doesn't, then it will be parallel. That's the only time it doesn't cross is because it's parallel. Otherwise, it will be crossing it. So to prove that, and that seems obvious if you think about it, but to prove that, then let's prove this thing. Okay, and to represent the surface, being this is being spun around. So if you think about it for some moments, then you eventually realize that the coordinate point on the axis, on the surface, will be r cosine theta, where r is x1 basically. Okay, but we're going to call it r instead, because for the parametric representation, then the x coordinate will be r cosine theta, r sine theta, and then f of r. Right, because x3 is f of x1, and so then we take the partial derivatives, okay, as we are told, calculate the normal. Remember, this normal isn't the unit normal. We just care about which way the direction points. We don't care how long it is. So we calculate the normal, and then divide. Yeah, and then we clean up the normal a little bit so it looks slightly better. It becomes anyway, and then we calculate we just got rid of the r because r is in every single component, and then we write down the equation for the normal line at some point. Okay, so we got this thing, I guess. What is that? Yes, we got this equation right here. The three coordinates, the three components of the normal line parameterized by t. Okay, all the other stuff is constants. So we have two situations. First, if f prime at that point at r0 is not 0, And then at that point, then we can set t equal to r over f prime r 0, because if we do that, then this and this will both become 0, right? So then we becomes so then the line becomes 0, 0, 0, and then something else, which a line like that is has let me think. What am I talking about? Right, that is not the line. That is if we choose t equal to that value. So this is a point, okay? So this point, which is on the normal line, is on the x3 axis, because it has 0 and 0 on the first two coordinates. And as a result, that shows that the normal line crosses the z-axis or the x3 axis when f prime of r0 is not 0. What if it is 0? If it is 0, then we can rewrite this line as this thing. Okay, and what is that thing? That is this line is a constant, and then the third variable varies, which is a vertical line. And vertical line, being that it's a vertical line, is parallel to the z-axis or the x3 axis. Yeah, and that should be the end of this argument. And I will show this to you again, and that should be good enough. Now next, let's look at problem 9, which I think is a short problem. The sphere is, of course, given that equation. I read it in big F form. So then that is normal, then is directly this thing, or you can divide it by 2, which happens to be the same representation of the radius. If you define the radius as a vector from at the point on the sphere minus the origin, which is 0. Okay, so then they're the same, and I think that's what the book wants to know, that if they're the same. And anyway, let's move on to example 11. Example 11 has we have two spheres. The two spheres have to intersect at a right angle like that. Okay, so we have two spheres. One is called x dot x equal to 1, which is the unit sphere. And the other one is also a unit sphere, but is located at a different point, at point A. So imagine there's one is located at origin, the other one is over here a distance apart. Okay, here's at point A. Now we know that for each they are normal at the intersection, which means x dot x minus a equal to 0. And then we can therefore write down that x dot a then equals to 1. Okay, and next we're gonna just do some algebra here. So x minus a dot x minus a at the intersection would be equal, let's multiply that out, which is equal to that stuff. And we already know that x dot x is 1, a dot x or x dot a are each 1, okay? And when you write it out, then you quickly find out that a dot a equals to 2, or magnitude of a is equal to square root of 2. And that is what we're searching for. These are two circles, each with radius 1, and their centers are apart by square root of 2. And that's the geometric representation. Well, anyway. That is, that's all I want to say about that. Next, let's look at problem 12. Problem 12, if you have three surfaces in the form 2, okay, form 2 is the big F. So three surfaces should have a common tangent line, okay, at a common point of intersection. So if we have three surfaces, they have the common tangent and a common point, then let's say we call the tangent line to be that thing. The three surfaces will have three normals, and each normal will dot the direction of the tangent line to be 0, okay? To be, Anyway, so being that the normal is perpendicular to the tangent, which means that the grad f, grad g, and grad h are all in a plane that's called x dot a equal to 0 or something close enough, okay? And they're all in the same plane where that's such that at that point, that's all I want to say about that. And anyway, so problem 13, what are we doing? Problem 13 about we have a curve, right, which intersects a surface. And at what angle does the curve intersect the surface? Okay, So then we calculate the curve. Right. So here's a curve, which we need to calculate. Well, first we need to calculate where they intersect. Okay. So after some algebra, we figure out that it intersects at these 2 points. All right. And next we calculate their normals or tangents or whatever. So the normal for the surface, which I calculated as this thing. And then down, let's look down here. The tangent of the curve, okay, is more tricky, and so that's where I'm messed up here, as I forgot what I was doing. Anyway, the tangent of the curve is you're gonna be dividing by 0. Which means this tangent is vertical, okay? In other words, if the tangent is undefined, we just let t goes to 1, which means the denominator, the whole value goes to negative infinity, so therefore the tangent is vertical, and so we'll write it as 0, 0, minus 1, and which is a vertical vector. Okay, and so the vertical vector, what was the original? Yeah, whereas this vector, the surface normal, is 2, 1, 0, which is a horizontal vector. So their dot product is 0, which means they're perpendicular, which means the curve hits the surface at an angle 0. In other words, it touches it in a tangent way. So I plotted this thing out as being that sounds interesting. So let me show you what I plotted on the Desmos calculator. Okay, here is the graph, see, and yeah, that is the blue thing is the surface, and the curve is the curve, of course. And as you can see, it touches the graph at some point, but in a tangent way. So the angle of intersection will be 0. And here is the graph on the other, looking from the other angle. When you turn it around, looking from the back. Okay, and I have the 2 dots here. The 2 dots are the points. That's where the graph to the curve touches the surface. Okay, and it looks pretty nice, isn't it? You don't have to graph this. I just did it because I thought it looked interesting. But yeah, for you to look at my graph is probably good enough, unless you want to play with Desmos yourself, which nothing wrong with that, of course. And that, I believe, is the end of this section. Well, let me show you the last part of my notes in case I didn't show it properly. All right, that's it.